Hi, this is Eric with Technically Speaking at Source Allies. Today we're going to be talking about advent of code. And not really talking about it so much as watching me stumble through attempting to solve day 11. Let's just get right down to it. So I was really nervous about this problem, so I took a sneak peek at the thing beforehand. But let's just kick it off. Some freaking advent of code. Let's go. So we got day 11 today, 11 out of 12, and we're going to be attempting to solve the reactor problem. So yeah, we got some elf setup, and the elves are doing things with server racks. Love that, those elves, they're always up to something fun. All right, but here we go. So our puzzle input, for example, okay, so we got 3 character tokens, it looks like, and then like a colon delimited thing here. So let's see, each line gives the name of a device followed by a list of the devices to which its outputs are attached. So BBB, DDD, EEE means that this device has 2 outputs, one leading to the device D and the other leading to the device E. The elves are pretty sure that the issue isn't due to the any specific device, but rather the issue is triggered by data following some specific path through the devices. Oh boy, graphs. And I I looked at this last night because I wanted to get my brain starting to think about things before we got in here. But yeah, we're definitely dealing with graphs today. So help the elves figure out which path is causing the issues. They need to find every path from U to out. Okay, so we got U and out over here. We have multiple outs. We have lots of outs. And we're trying to find all of them. All the paths from U to out. Data could take the connection from U to B, then B to D, so on and so forth. Okay, so let's see if we can get going with the sample code here. So I got my little OCaml set up. I'm using OCaml for this. It's such a fun language. I've got my little project workspace. Ignore the fact that I've only done days 1 through 3 here. It's been a busy December. Haven't had as much time as I'd liked to work on this stuff. Let's download the sample. So we got I'm gonna get my little AOC CLI here for downloading the thing, which hopefully Nix will be helping me with that here soon. All right, and then we can go AOC. Oh, we gotta have the session. You know what? Forgot about that. I didn't set that up ahead of time, so we're just gonna skip it. We're gonna download it manually, or download air quotes. We're gonna copy paste it. So let's go over here and let's touch sample, and let's just get our sample code in here, and let's get to parsing this. I think realistically all I'm probably going to get done today is just the parsing of the input, but we're gonna try. We're gonna get as far as we possibly can, because advent of code's all about having fun and just tickling your brain with some of the cool problems that they have, and at least in my case, using a language that you don't get to use very often. So let's, oops, I'm not in the home row. There we go. So let's create our input reading thing. Read lines, and then this is just kind of boilerplate I've been copy pasting from the other ones. So we can just keep doing that. Let's go get our, or I guess I called it read input over here. So we'll take this, we'll have our read input, and let's clean this up a little bit. Let's see, file name, and we want to return, yeah, string list is still fine, I think. So we'll fix this, and then this was from the other problem, so we'll get rid of that. And let's see, I've typed string, but an expression was expected to type string list. Input all. Let's see, we want input lines. There we go. So input lines will give us a string list. All right, so now, and let's see if we can get our little thing going. So if we do Dune exec, and we'll say day 11, and we want to watch. Great, now it's telling us about this unused function. So let's use it. We'll read input, and we'll start with sample, and then let's just get this to be printing back out. You know what, and Copilot's right. I'm going to turn off Copilot. I don't want Copilot helping me. What do we... There we go. Copilot is now disabled. Thank you, Copilot, but we're going to do our own thing. All right, so we got the sample printing out, so love that. And let's get to parsing this. So let's have a parse function. Just knowing that this has to do with graphs, I know that we're going to want some sort of graph structure. And usually we have, at a bare minimum, we've got nodes. So we need to have all of the graph nodes. And I think we can do that by... yeah, so on the left-hand side, everything to the left of the colon is a node, and then these are sort of the vertices, I think. So this is what we'll start with. Yeah, so this is just a list of all of our. This is basically creating our graph, and then we'll be starting over here. I think if I'm understanding this correctly. So how's that work? So this is we start with U as a vertice or vertex. Yeah. Elf hastily attaches label, it just says U. Every path from U to out. Data could take the connection from U to BBB. Okay, so maybe I have this backwards. Maybe left-hand side. Let's see. Each line gives you the name of a device followed by a list of the devices to which its outputs are attached. So these are input to output. So maybe I'm just confused at how we start at U when U is an output. And we're trying to go from U to out. So data could take the connection from U to BBB. So we have, oh, I'm blind. U is on the second line here. So this is the start. Yeah, so this is just our graph, and then we know that we'll eventually start at U when we get to that point. Okay, so there. Now I think I'm got that figured out. So we do want to create a mapping of node to vertices, I think. So we want to have, and I may need a data structure for this. I try to avoid data structures in Advent of Code if I can, but let's just see how far we can get. So let's just call this parse for now. I'll probably have a better name for it. And I think we have our string list. So let's just get our lines. We'll say it's a string list. And this function is going to do some stuff. Let's just call it down here. So we'll say, we'll pipe this to parse. So read input, sample goes to parse. What is it mad about? Unbound value, oh, because we haven't finished over here. So, and now it's mad because parse is returning a unit, and this is attempting to iterate a string list. So let's see, in our parse, what do we have to do? So we have to get, for each line, so we'll get a list.map to start. I'm not sure if we'll stay this way. And this will give us a line, and in that line, we're going to we're trying to match a pattern. So we want to parse the left-hand side to get the node, and then the right-hand side and split on spaces to get the rest. So let's just start with that then. We'll do a string dot split on char, and let's split on the colon first. So this will give us, oh, and we need to pipe line in here. So we'll split on the char, and then that should give us a char or a string list. Yeah, string list, and then we'll want to take the first one. So we'll do like a function, and we'll map. We'll match on two parts. So we have A and B, and we'll say that A should be our node. So let's see. Let's just start with. Let's just do a tuple for now. So A will be our node, and then B will want to split on. I think spaces seems. Yeah, I think splitting on spaces will give us our outputs. So we'll do string dot split on char, and we'll just give it the space char here. All right, and then this pattern match is non-exhaustive, so we kind of expect this to always pass, so we'll just say that the discard case is going to fail, and we'll just say fail with heck. There we go. All right, so now that's happy. Let's see if we can format this, make it a little bit better. Oh, we gotta We're going to pipe our lines to the list map. There we go. So this gives us a tuple of string list. And if we want to be able to print this out, I like to be able to visualize things as I'm working. So let's see. If we have this string list, let's see if we can just simply recreate it in here. We'll do a function that has, let's see, this is our, well, it's our graph really. And we'll say that in order to create basically a list of strings, we'll just combine them together. So our graph, actually let's switch this to be a list.map, and instead of that, this will now be just a single line, or a node, I guess, is kind of what it is. And then we will, oh, this is a tuple. Yeah, so we can deconstruct the tuple, so we'll get our actual node, and then our vertices, we'll say like N and B for now. I don't think I'm going to keep this code. And then over here, let's just print out N for now. This should make it happy, and then we can just discard. And I'm hoping that we should see our output more or less echoed back to us. Perfect. So I like where we're at. Those are our nodes. So let's see. Maybe now we have a data type. Let's create a simple little node type, and this is going to be, I guess it could be, we could keep it as a tuple, and we'll say, I guess label, I think is what these are usually called. We'll say label is a string, and then the vertices are, well, let's keep it simple for now. We'll say the vertices are a string list, because that's basically what we have, and we don't know that we need anything more than that yet. So over here, instead of a tuple, let's just see if we can create a new thing here. So we'll say label equals A, and vertices equals string dot split on char space B. There we go. And man, I does not like the formatting here. Oh, you know what? I don't think, oh yeah, I don't have OCaml format set up properly. So we'll just touch .ocaml format. There we go. And if we run that, oop, oh, what's it called? It's like something in place. I always forget. In place. There we go. Exclusive with in place and output. Okay, so I think if we just do OCaml format in place. Must specify at least one. Oh, yeah. And then I want the current directory. That's not the current directory. This is the current directory. Just kidding. The funs of recording a video. There we go. I was going to say, I was like, that was getting kind of long. I thought it would normally format onto multiple lines here. Okay, so perfect. So now we have our node list over here. So when we recreate our little doodad, we can deconstruct again. And instead, we'll say, let's just get the label out of here. And let's label, and this should get us back to where we were before. Oh, I stopped this from running. There we go. And it's saying that we haven't done everything, or we haven't deconstructed everything yet. Oh, how do we discard? Is it vertices, vertices? Vertices, and then discard. There we go. That's what it is. Okay, so we're back where we were before. So we've got our nodes getting printed out, and we could instead, what if we just switch this and say this equals that? Oops, I accidentally hit insert. And then we'll get our vertices, and instead of ignoring them, we'll just say like string dot, oh, what is it? It's not join, it is combine, concat, string cat. That's what it is. Or is it? String, no it's not. I forget what the standard string module looks like. This is one of the downsides of picking a language you don't work with super often for advent of code. But we're making progress. So once we have all of our nodes, I'm hoping that it shouldn't be too bad to basically count them, because I think our goal is to get all of the paths from U to out. And yeah, we're just counting the number of paths. So anything that successfully gets us from U to out. Oh boy, this is going to be fun. Oh, well, what am I saying? In OCaml, strings are, well, okay, we've got that. You know what? Let's quit beating around the bush. Let's go get the standard library pulled up. OCaml string. So we'll go to the string module, purple ink. I've been here many times. We want to concatenate. Oh, it's just concat. Of course it is. It's not cat. It's concat. String dot concat, and then now we'll give it our separator and vertices. Okay, there we go. And now we're printing out our vertices. Perfect. So now we have a list of nodes. So we could technically create. Well, that is our graph. A list of nodes is our graph. So I think we need to figure out how we're going to count these now. We may be that far, or maybe I'm getting ahead of myself. But we have a list of nodes and their vertices. So yeah, let's see if we can match the sample. So our goal is to get 5 from this sample input. So data could take the connection from U to B, then from B to D. So, one single path is all the way from U to out. So how do we do that? So we need to find U first. We need to find U. And now I'm thinking that, yeah, we're a little bit premature saying we're done with the graph structure, because we don't really have a mapping. We just kind of have the vertices, and I feel like we're probably going to find that in a second. Find that out in a second. So let's start P1, and we'll say we have our graph, which is we'll be explicit with our types here. We'll say this is a node list, and this is going to equal something. We're going to do a thing with it. So down here. Do we want to put, no, let's leave that for now. So in our node list, we need to find, so we could just start by saying, let's just keep it simple. We'll find U in the node list. So we'll say find, and it'll be a function where the node dot label equals U. So this should give us, and then if we give it our graph, look at this graph. This should find, yeah, okay, so node list to node. So if we go down here and we pipe the result of parsing to part 1, now this won't be correct because this is just a node. So we'll say a function of node, and this goes to print end line, just n, I think. Oh, end dot label. End dot label, there we go. And what is it mad about? It's mad that this is unused. Too frickin' bad. So we'll switch this up. We'll say label vertices equals discard, and I can't spell, but it's fine. So now, there we go. Okay, so we found U. So we found the start. So this actually, let's maybe extract this. This is kind of its own little function. Doesn't need to be anything more. So we'll say find U. This is giving me big Charlie vibes. His Slack handle is like Charlie Hall and then in parentheses U, because that's how Charlie works. So now we should be able to plug this back in over here and wind up with effectively the same output. Yeah, U. So I just refactored a little to get rid of the explicit graph thing, because OCaml has partial application, and it's amazing, and I love it. So now, P1, if we find our U from the graph, and maybe we'll say graph and pipe it to find U. So now we have our start. So we need to find out. We need to find all of the outs, because there's multiple outs, and we need to count the number of those. So we have a single graph, and we want to calculate multiple paths from that graph. So we need to iterate over something in order to get those multiple paths for counting. So let's see. So now that we've found u, so we have a function that has u, and now in this scope we have access to both u and the rest of our graph. So what do we want to do here? My first thought is we want to try to find all of the outs, which that I think should be pretty trivial. So we have our u node, and we know the labels here. Okay, yeah, so right, we know what this is connected to. So I guess the simple case, so we could see if any of these vertices contains u. So we could say list dot contains. I thought there was a contains. Maybe it was something else. List dot. There's always exists. There we go. That's what it is. List dot exists. And we'll say, let's say, like contains out. Just to. This is our node, and we'll say list dot exists. Fun. Oh wait, no, that's what we're doing right now. N dot vertices. There we go. List dot exists. Fun. Oh, we can just say equals. Actually, this is just equals out. There we go. So now we can go over here and say contains out u contains out. So this now is node list to bool, which is not quite what we want. So we could say find instead. So where are we at here? So we either find out or we don't. And if we find out, then we're done and we have a path. So I think maybe let's, yeah, so it feels recursive. It feels like we'll have a base case where we've either found out or we haven't. So let's see how that looks. So we'll call it like, I don't know, let's just call it find path for now. Something just to get us moving. And find path will accept a node and a graph, I think. So that's just where my head's at right now. So we'll say find path from the current node using this graph. And so we're basically saying match well, do we want match? It's more of an if contains out node, then, and OCaml literally has a keyword then. So if contains out node, then we're done, and let's just return node, and we can say else. We keep searching, and we'll pretend that this is a recursive function. So we'll say let rec, and we'll find path. Okay, so now we need to get the next node. So this is wrong. But we'll get it out in the open. So we need the next node. So okay, so this is starting to make more sense. So this is where our iterating comes from. So this is feeling like our actual implementation. Okay, well, I'm thinking I'll probably combine this with P1 in a second here, but maybe not. We'll see. So this is, rather than returning node, I think we would just return like 1 because we found a path. I'm thinking that we'll want this to be an int. This will sort of be our count. So find path, how do we get the next node? So let's have a function for that, because that's effectively what it is. We want to get the next node, and I don't know if we'll need the current one, but we'll accept it just for now. And we will say, for now, this is just going to be equal to node, just so that it will compile. And over here, we'll say this is now really going to be next node graph, This looks a little weird. I don't think it's going to stay this way, but it's what we got for now. So if we want to have this actually running again, can we say find path u graph, and this returns a node list int. Oh, we're not calling p1. P1 find u. Yeah, so we don't even want to call find u down there anymore. And the result of p1 is an int, so we honestly can probably just pipe this to like, what is it? String of int, and print end line. All right, there we go. And it's just complaining about this not existing, so we'll do that. And it says there's one error somewhere. I feel like it's probably just infinitely recursing, and yeah, that's exactly what I was doing. I created an infinite loop that, I don't know if you can hear in the recording, but my fans just kicked up. Whoops, infinite recursion. Okay, so now that we have this, now we have this nice little scope where our only goal in this function is to find the next node in this graph. How do we know what the next node is? So we can look at all of the vertices of the current node. We effectively want to loop through them. Yeah, this is still feeling wrong, but we just need to get some code onto into the file. So we'll start by like iterating through the node vertices. We'll say like list dot, I don't know, we'll just say map. I like map. We probably want fold, actually. Yeah, I think it'll be a fold because we want to basically get this down to a single value, and fold will do that. And I guess, yeah, OCaml calls the default fold left because, I mean, that's really what it is. So now we have fold left, and we have our little folder function, and we need an initial value, which I guess if we're going to go with, yeah, maybe fold's not the right idea, but I think the initial value will be our node. Only because the end type is we're trying to get a node out of here, so that just makes the types work. And we'll say now function from our accumulator and the current node. I guess this is actually the vertice. So let's say that's v. So the vertice and then the node. So I think I'm iterating over the wrong thing. Because we want, from the vertices here, we want to map them to a node in the graph. So we actually want to find in the graph. So we'll say list.find, and we want to find, oh, the one that contains out. Yeah, I think my structure's all wrong here. We'll probably circle back and clean it up. But I'm going to keep going with this train of thought, at least for the moment. And this should be our graph. And we'll say list.find, and now we're looking at a node, and we want to say where the current node vertices list.exists, one where the value is equal to the node label. So we'll say in vertices where one exists that has a node label, that'll give us the next node. And perhaps this is, maybe the reason that this is feeling awkward to me is that we may not find one. It's always a possibility. So I think list.find, not found. Yeah, okay, so list.find raises an error if it can't find something. So I forget if there's an option that, oh, find op, perfect. That's exactly what I was looking for. So if it can't find it, it'll return an option type instead, which is more what I want. So now inside of here, let's say we have a function, and this will just say, did we find a node? And this will be, we'll say this is to do. Else, if none, fail with, I don't think this would be a fail. I think this is kind of our done case. Done question mark? We'll see. So fail with, and let's just make this n.label for now. So I think everything compiles at least. And I feel like I still have an infinite loop in here, but we'll see if that sticks around. So let's see. This is looking terrible. Where are we at? So, oh, and I hate the default formatter, how it makes things so cramped. So part 1, graph, we find u, so we find our starting point, and at least according to the sample input, that's the only starting point. I hope that doesn't come back to bite me. And then we want to find the path, and this returns an int. So we need to create an int out of here. Find path, next node, so this will return, yeah, so we want to say, this is just 1. It feels like it's just 1. Or no. We want this is recurse. We've already recursed. We're calling find path with the next node. How about we just run it? This is gonna break, and I want to see how it breaks. Exception, failure, B. So that's right here. So we did get here. So that's cool. We did find the next node. My brain is just not processing what we have to do here for some reason. So now that we have our next node, we want to see if it contains out. Otherwise we keep going, which is what we have here. So if next node, if we found the next node, yeah, I think this is just backwards. Find path. Yeah, we want to see if we can get the next node, and we only want to recurse if we found one. Yeah, brain is just not processing this. So I think this is just complaining that the rec flag is unused. So let's switch this to say find path n, not m, n graph, and where's the one error? Technically finished, and we got 1 because that's all we ever return. So let's see. I think, yeah, we do need to accumulate. We do need to accumulate in here. So let's just say there's our accumulator. Yeah, this find path is, I think, kind of turning into our accumulator function. So we'll find path there. You know what? Yeah, can we just list.fold left, and find path is kind of our thing, and then the initial value will be 0, or the seed. Let's see. So then, and that's just our starting point. Maybe fold isn't the right method for this. So what do we got here? Maybe we should make this compile. So if we didn't find anything, this is kind of 0. So let's just change that to be 0. And then I think we can pipe back to find path. And does this have to be in parentheses in order for that to be happy? No, it was a different problem. Different problem. Because we're returning random things. Oh, it thinks accumulator is a node, that's why. I think my recursive function is a little weird here. I think this accumulator was a bad idea. I think I'm mixing 2 paradigms, either recursion or looping. You typically only pick one or the other. And maybe you should have like some test data or something like that. So maybe this should be like find paths. Maybe this returns a list of paths. And when we find a node, I think this still is the recursive case. Yeah, my brain is just not processing this very well. So contains out is where we found this is our base case, and this does exit the recursion. Otherwise, we keep recursing, and we do that second because of the hope of tail call optimization. I don't know if that actually applies here, but supposedly it's better. So if we have find paths, yeah, we want to keep going until we hit our next node and then contains out, and we want to sum them all up. So I think we do need an accumulator of some kind. I guess recursive functions can still have accumulators. And this is why it thought it was a node. My brain is starting to work again, I think. So we add 1 to the accumulator. Oh, no, wait, that's not true, because we haven't finished. We only add when we finish. We only add when we finish. Otherwise, yeah, okay, and paths. Paths U graph, and then the accumulator starts at 0. Kind of surprised that worked. So supposedly we found one path. I don't trust that. Let's use OCaml's beautiful little side effect pattern to print. Actually, let's do a format print. So printf, and we'll say let's print out like the node label. So we'll say %s, and we'll do the node.label, and we'll see where that. Oh, we gotta have in. There we go. In. Let's get our new line in there. There we go. It's a little bit more readable. Well, kind of looks like it's working. So let's see. So we have U to BBB, and was that U to BBB, then BBB to DDD, which we do have, and after that, DDD to GGG and GGG to out. I'm a little surprised. I didn't expect that to work, but it does seem like we've correctly counted one path. So now we just need to count all the paths. So how is that going to work into this? Honestly, I was not expecting to even solve that much, but hey, always a good time when we get further than we expect. So 1 plus the accumulator, and then we sort of exit. So we're done. So we're missing that point where we're looping over the vertices. Excuse me, and I think that's because we're just finding the one that equals the label. So I think this is kind of in reverse. This isn't going to find, okay, so I think we really want the next possible nodes as opposed to simply the next node, because there could be multiple next nodes. So let's go down here and let's change this, and we'll say this is next nodes. Get the next set of things that we want to loop through. So maybe instead of find op, maybe we want like a filter, I think. Next nodes. So maybe my terminology is kind of confusing me a little bit here. So node is really, what are we looking at here? Because is this U or is this something else? So I think currently, at least up here, this is referring to U, and we look through all the vertices on U and find ones that, yeah, so I don't think that's right. Yeah, because N, yeah, we're checking to see n.label exists in the node vertices. How is this even currently working? I don't understand my own code. Graph, list, find, opt. Oh yeah, this n is different than node. That's where I'm confusing myself. It's why you pick good variable names, because it's easy source of confusion. So yeah, so n is referring to the next one, or the one from the graph, the one that we're not currently at, and node is U. So all the vertices on U want to see where list.exists, the next label. So I think instead of, yeah, I'm still thinking this is a filter. Let's do filter, and this now just needs to return a Boolean. So it's kind of okay as it is, actually, because it was returning a Boolean before, and now we have a node list. Okay, so perfect. So now next node. So now we want to basically map this function instead. So we want to say list.map, and that'll be our function. Obviously, that's not quite right. What are we missing here? So n we're expecting to be of type node, and this returns, yeah, I don't think I'm gonna, I modified the wrong one. Actually, we can salvage this. Let's move this down to filter. There we go. So now the names line up with what the functions actually do. And we want to call next nodes. And now, there we go. So now we'll list dot map, and it's always easier to start with a function. We'll just call x. X should be of type node. It is. So now we can do our function. I'm just kind of confused why this has so much red, because we're basically just matching x with that. Expected to have node option, or let's see. Expression has type node list, but an expression was expected of type node option list. Oh yeah, right, because there's no sum anymore. Okay, duh. We're simply looping through them and attempting to find the next one, actually. Okay, so that's what this really is. So this is a function of the current node, and we want to find paths with the accumulator to the node to the graph. And still not happy with that. Probably because we need to flat map, which we, rather than flat map, we can just do list.flatten. I thought. Just kidding. What do we got here? Yes, we're still returning an accumulator. Oh, right, because this has to... we'll map to that. That'll get us a list of things that we just need to sum them all up. Fold left, and we'll do plus. And we'll start, the original value is 0. There we go. Now it's happy. Well, except for this. It's not happy about this, but everything else is happy. Wow, I'm surprised that worked, if I'm being honest, but we did get 5 as the end result, and I don't think we want to keep printing this out. So let's stop that, let's use our answer, and then let's see if that's good enough. It might be, and then we may be able to actually have something done here. So we'll go down here, we'll say here is our input, we'll paste the whole thing, and we'll run our program against it. And fingers crossed, let's see if we get it. 649. Okay. So that's our answer. And let's see if it's right. So 649. Woo! Oh my god, we did it. That's insane. I can't believe it. Yay, we did get part 1. Which was further than I thought I would get. So yeah, this has been Eric with Technically Speaking at Source Allies. If you have a topic you want to see covered, comment it down below. And definitely check out our website, sourceallies.com, to learn more about us. Thank you, and I hope that you do Advent of Code too. See ya!